Hello everyone, I'm Inoq and welcome back to another video for the series. And today I brought a problem from IMO. It's problem number 2, so I believe it should be considered hard. But it's been a while since this test came out. So it was like year 2001. So I think it should be equivalent to like um, level of like number 4 in like recent years. Not like I'm not sure. I didn't solve every IMO problems. If I did solve them, then I should be a genius, but like not. So and also like you might have noticed it, but these days I started saying like hello everyone, welcome back to another video. Wait, hello everyone, I am Inoq instead of hello everyone, I am Thingy Tree, and that's because I am actually thinking of changing the channel's name because it's not that unique. And also, like, my friend said, if they want to find Thinking Tree, then they need to like scroll down like a lot. So that's why, yeah. And then without further ado, let's start this problem. And like always, I couldn't like completely check the solution. I just simply took a glance at the AOPS solution, but I saw a keyword. It was Herder's inequality, and I saw an inequality, and I just stopped right there and then started making this video because I think gaining the keyword Herder's inequality and the actual inequality involving it is a big thing. So maybe after that I can continue by myself. So I stopped looking at the solution, and if I make any mistake or if I did something mathematically wrong, please feel free to leave it in the comment below. And also, like, the original solution was like really short, so I was like it didn't include every steps, and I don't know who actually wrote the solution because like usually in AOPS when there's a solution here they usually leave something like they do this, and I will usually do Mathicom because that's the ID that I use. But no, I couldn't find this, so maybe this might be the official solution. Maybe. Okay, now let's start. Let A, B, C be positive real numbers. Prove that this is true. Now, let's rewrite this one first. So we can rewrite this as over a squared plus 8bc. Oh, what? I don't know why this is happening, but my pen is not syncing well even though I reboot it multiple times. I think it's time for me to change it. So we need to prove that this is true. Now, I don't really like the denominator here. I don't like it because you have square roots. Then why don't we try multiplying? Why don't we actually try multiplying it 2 times? Like this. Then we might somehow magically get rid of the denominator. Of course, we cannot do it directly because it's not a single term, a cycle of this term. But maybe this might give us something. Now, I think it's quite self-evident that we need to use Herder's inequality here because that's what I said we are going to use. Herder's inequality states, it's been a while since I defined Herder's inequality. I think I should do a little more review there because I couldn't study much on algebra these days. It doesn't have to be 26 terms. Wait, are there 26 alphabets? Yeah, there are 20. I just counted, and there are 26 alphabets. I just wanted to be precise, so it doesn't have to be 26. It could be more, but there are only 26 English alphabets, so we stop right here. Wait. Oh, I'm not sure if this is like the formal definition, but this is at least how I studied. We have a sub I, lambda sub a, b sub I, lambda sub b, all the way up till z sub I and lambda sub z. Okay, then why do we need to use this? And the reason is because it's quite simple, because we're going to multiply these two terms, and I think it would be great if we have 1 over 2 and 1 over 2 here, so that we can merge them and get rid of the roots. However, I'm not quite satisfied with the results that we get, and that's because this is what we get as our result. But I mean, it's not that clean. It's not that clean. But we know that this is true and it's not that clean. Then what can we try? Actually, I think I need them. What we can try here is actually multiply. Just simply multiply it. Like a squared plus 8bc. That way we can get rid of the denominator. But here's the catch, we need to change everything into 3 and 3 so that they line up here, and then we can get rid of it. Then we will have this one. I don't like it. Let's multiply a here. That way we have this equals a, and that's really, really clean. And now we don't know that if it is greater than or equal to that. It's actually greater than or equal to the term that we just multiplied, which is, no, actually, let's use harder from here. I'll just do one term, and we know that it will be the same for the other 3 terms. We can just use the cycle. So if I do for one term, we have a squared plus 8bc 1 over 3 times, no, actually, times a over root a squared plus 8bc times a over plus 8bc and 1 over 3. So these cancels out, we get a. So we have a plus b plus c here. Oh, that's very, very, very nice. Now, because we're looking for an inequality that's related to this, let's just cube our both sides. Then it will give us a times cycle a squared plus abc. I will just use this notation because there's no reason to repeat. Okay, so I actually don't know how to continue from here, but I think I can do it. Okay, so we know that this is greater than or equal to 1. And we know that this is also true. Wait. No, we don't know this one yet. If okay. Okay. I will just write it. A squared plus 8bc if this is greater than or equal to like a squared plus 8bc, then plus 8bc, then, and this is quite self-evident, I think, and that's because because we know that this thing must be positive because A, B, and C are positive real numbers, we can cancel them without changing the sign. So we have this thing is greater than square is greater than or equal to 1. So this is either this or this, but it must be this because this doesn't work because A, B, and C are positive real numbers. So this is true, and I think that was quite self-evident, but just for clarification. Okay, then this is true. If this, then this. So we just need to prove that this is correct. In other words, we need to prove that wait. If okay, I think okay. If we somehow prove that this is true, then we prove everything because we can write this and this will automatically be true. And the reason why I paused a little bit in the middle is because like I wonder what if this thing was like swapped, so this thing goes in here and then we have something like this and it goes in here. But now that I think of it, I don't think that will work because Hurder's inequality also have the time when it's like equal, so it does have an equality condition, meaning it's more likely for this thing to be true than vice versa. So that's why I think this could be correct. So okay, if this doesn't work, then let's try the other one that I mentioned. Oh wait, the other one, then it doesn't work, so we need to directly derive it. I cannot think of it right now, like how to derive it if this thing doesn't work. But I'm pretty sure this should work because if it doesn't work, it will be like this problem will be way too hard. But it's IMO, so maybe. We might as well have to expand it, but I don't think that would be that bad. So if this doesn't work, then we need to expand this side, but it would just be painful. Let's just try this one first, hoping that this will work. Okay. I will just write this in a new place here. Or actually, I'll move it here because I want to expand them. What do you get if you expand this? What do you get if you expand it? We can definitely use multinomial theorem, but I don't want to use multinomial theorem here because I know that it will not be that difficult. A cube plus b cube plus c cube. How many a squared b's do we have? We have 1. We also have a squared b. Okay, c. Okay. We have 3, right? A. Yeah, we have 3. Oh, what? I cannot believe that it took me that long to think about it. But notice that it is cyclic, so we have c plus a plus b. Okay, then we use this form, The other form that we can have is this one, right? So we have 1 variable, 2 variables, 3 variable. So I mean we can double check it every time. How many of a plus ABCs do we have? That's 1, that is 2. I think it should be 2 times. Wait. Oh my goodness. 2 times. 2 plus 2 plus 6. A, B, C. How many terms do you have? Let's count it. 1, 2, 3. 3 plus 6 plus 6 plus 6 plus 6 equals 27. And how many terms should we get from here? Is 3 times 3, so it says 27, so we counted everything. Nice. I just did that to double check if we did count everything. Okay. It's a cube plus 8. Oh, wait, actually I think it'll be pretty nice. I just hope it works. Let's just hope that this works, or we have no other choice than to face the pain. Okay, b plus c plus 3b squared we have 24 minus 18abc greater than or equal to 0. A squared b plus c plus 3, oh, just b squared, c plus a plus 3, why am I 6abc. Let's distribute them equally because we know that they are cyclic, like this. I hope this works, like magically somehow. I think it works. Nice, great. But let's don't be happy too soon because it might not work. Okay. But let's just try. Oh. Wait, what? Actually, I think it works, but I need to rewrite them. But it's okay. Let's just factor them. So by a, if we factor it, we have b and c, right? So b squared plus c squared and use 2bc. So let's use b. We have a squared plus c squared minus 2ac plus c is a squared. It's b, right? Greater than or equal to 0. Let's see if we counted everything. How many terms do you have here? One. Wait, what? We did count everything. Okay. So we have a times b minus c squared plus b times a minus c squared plus c times a minus b squared is greater than or equal to 0, and this is true. Which means this thing is true, which means we can write this. What? ABC, which means this is true, then this is true. Thus we proved our inequality. Nice. I'm glad that it worked. Okay, so like always, I think the kick of this problem is trying to just thinking of this thing to get rid of this and also this one to make something cleaner and then relate that to Harder's inequality. So I think that was our first kick here. And I don't think we don't really have the second kick. It was quite obvious from here on, but like writing lemma maybe, and then other calculations from here, they were quite obvious. So yeah, I think I learned a lot from this inequality, because who would have ever thought of using Herder's inequality from here? I mean, you might have thought of it, but I was not able to. So yeah, I learned a lot from this problem, and I hope this video was productive and meaningful, and hopefully meaningful to you. And thank you so much for watching the video, and I will come back tomorrow with another fun problem. And thank you and see you tomorrow. Bye.